Okay.
Good morning, Professor. It's our honor to introduce our project. Coffee Whisper, Metal Royal Formation Machine with IoT. Introduction. When we learn about the royal formation machine for the first time in our mechanical manufacturing class, we were all fascinated by its theory and potential application. The only downside, however, is that the royal formation machines on the market now are mostly large and expensive. Eager to learn more about this incredible machine, we decided to make a royal formation machine that is small in size, low in cost, and can allow users to operate with numerical control at the same time. But how can we make one such machine out of thin air? Before we put our theory into foot. First of all, we use text drawing to make a sketch. Then we do program coding in Python, so that the machine can convert EXF text file into G code. After several attempts, we make our finished product.
Equipment, wire formation mechanism design and manufacturing process. Before we complete our machine, first of all, we need to make the wire formation mechanism. Let's take a look at our mechanism design and manufacturing process. As you can see, this is our wire formation mechanism, which uses the lower steel motor to drive the upper line folding shaft to rotate and bend the material. We deliver from the metal line gun. For our steel motor model, we choose the model 42 steel motor and increase output torque with 1 to 5.18 planetary reduction compartment. Combine the steel motor and the line gun, we now have a wire formation mechanism. The following is the complete design figure. We want to test the deformation of the material when the transfer edge of our forward line guide bears the measurement force of the motor. After we calculate the variables, we discover the measurement to be 107.93 Newton. Then we use simulation to calculate the measurement deformation of our material to be 0.2437 micrometers, which does not have much impact on our material. Now that we have the wire formation mechanism, we will move on to make our product more realistic in terms of 3 dimensions. S6 rotating mechanism design. To achieve the goal, we make an S6 rotating mechanism. Its function is to allow the wire formation mechanism to rotate and fall into a 3-dimensional shape. Screw driving mechanism. Another design that is equally important is the screw driving mechanism. It is designed to make our machine move up and down, so that we can bend anything in a negative bending angle and cut the lines.
Wire cutter head design. Next, we also need to come up with a wire cutter head. It is used to cut off the folding shape without manual cutting, which will come in handy when the machine goes into mass production. It is the mechanical drawing for our machine assembly.
Circuit configuration. To help the preliminary machine move smoothly, we turn to the Arduino and the RAMs of the 3D printer that we have learned before as our circuit system. Arduino parameter setup. In the above picture are the control parameter we modified to control the motor. As you can see, here is completed machine we assemble. After assembly is completed, we can now try folding out the product the way we decided. Experimental result. Wire formation experiment with different wire folding pin diameters. In order to find the best condition to make perfect product, we spent months conducting numerous experiments. During the process, we repeatedly use wire folding pin of different diameters to match with line guides of the same diameters. We found that it's accurate. We found that the bending angle are almost the same.
Wire formation experiment with different light guide. We use light guide of different sizes with metal rod of the same diameter to carry out our experiment. We find that the smaller the diameter of light guide is, the smaller the folding angle of light guide is.
Experiment with wires of different materials. To find out more about the effects of wire material on the product, we collect a few different materials such as metal wire wrapping paper, copper wire, iron wire, and aluminum wire. Here are the wires we have folded. And our experiment proved that our machine can be used to fold and shape the wire of different material into any form we design. No doubt, the machine is versatile as well as cost-effective. Wire feeding mechanism positioning repeatability experiment. Next, in order to test the precision of our machine, we feed aluminum wires of the same length into the machine at the same speed. We repeat the same experiment for at least 20 times, and we find that its accuracy can reach within a range of 0.01 mm, which is a very promising result. Wire feeding speed experiment. To make sure that the machine can work stably, we do more experiments in terms of different speeds from 100 to 5,300 mm per minute. During the process, we discovered that the machine can remain stable when speed reaches 3,200 mm per minute. Its accuracy is still within 0.01 mm. However, when the speed is higher, we can no longer acquire the same precision. Trim point positioning experiment. We conduct this experiment in order to find the best coordinate point for the wire cutter to get a clean cut. This way, we can prevent accidents from happening. To achieve this goal, we have find a way in which the machine will create the smallest spur when cutting the wire. At the end, we find that we can get a perfect edge when G-code is set at 45. Software. Below is a setting for wire length and the direction of angle bending in our program coding. In order to get right results, we conduct many experiments and repeatedly correct the errors between actual bending angle and the set value of x-axis. The formula has been calculated line length error, better dot product calculation angle, better cross product to determine the direction of bending angle to be clockwise or counterclockwise. This is a program interface that we developed. Users simply have to save the joint cat join as a DXF file, and then import it into our program before converting it into a G-code, so that the machine can read the bending code. Here is a comparison of our finished product and CAD files. IoT. Next, come to the part of our choice of Internet of Things. IoT. At first, we have 4 choices. Not knowing what to do, we consulted our teacher and did a for comparison. At last, we came to an agreement and decided on ESP01. Conclusion. Overall, our machine has a graphical function. Also, by using Python to write DXF code, we can easily convert code into G code. Therefore, the operation is simple and straightforward. On top of that, our machine enables users to fold out the 3-dimensional model. What's best, since we are all high school students, we make all the machine parts from the ground up on our own, which means the cost is relatively low. That's all.
Thank you.